Hello. So today we're going over the rest of chapter 12. So we're going to look at the rest of the types of solids and some more calculations. Our learning objectives today is we want to be able to do calculations for both ionic and metallic structure. Those includes density calculations, length of a unit cell, empirical formula, and packing efficiency. We'll look at mostly doing these with metallic cells, but we should be able to do this with any type of unit cell as well. Next thing we want to do is be able to describe the properties and characteristics of an ionic unit cell. So we're going to look more at ionic unit cells themselves. We'll also be looking at covalent network cells or solids. So you should be able to also be able to describe their properties. We want to be able to take that ionic solid and describe its structure using its ionic radius and empirical formula using its structure. We're going to look back at valence bands, conduction bands, and band gaps. So band theory, we looked at it for metals. Now we're going to look at it for semiconductors and insulators. We also want to be able to explain the difference in band gap between an insulator and a semiconductor. And, of course, we looked at metal having no band gap. And what does that mean electronically for that substance? We also will be using our periodic table to determine relative band gaps and calculate wavelengths based on band gaps as our last thing within that. We'll be looking at P and N-type semiconductors, so we're going to take our intrinsic semiconductors, which are semiconductors that are just natural, and then we're going to add additional elements or substances within those semiconductors to make extrinsic semiconductors with different properties. So we want to see how we can make those different semiconductors and what that means. And then we're going to be looking at polymers and monomers. We want to know what polymers and monomers are and be able to figure out the monomer structure using our polymer structure or empirical formula. And then how the different types of polymers are formed, our polymerization reactions, and explain the polymer structure. And then we'll be able to describe nanostructures by the end of this class. So what happens as you go from a bulk structure, so a huge three-dimensional structure, to a nanomaterial, a material that has at least one dimension on the nanometer scale, so 1 to 100 nanometers. And then relate band gap size to relative size of the material for a semiconductor. Okay, let's look at our unit cell densities. So density, important information to tell about a unit cell. We determine our unit cell density by taking mass of our atoms within our unit cell divided by the volume of our unit cell. We can get our mass by taking the number of atoms within the unit cell, multiplying it by the mass of one of those atoms. We can do this for both metallic solids as well as ionic solids. And then to get our volume, we're going to take our cube and cube the side. So length times width times height. A cubed will give us the volume of our unit cell. We're only going to be dealing with cubic unit cells, so we can always use A cubed. Okay, so let's see. Can we do this? So we've got a face-centered cubic cell. That face-centered cubic cell is platinum with a radius of 139 picometers. Let's just change this to black. Okay. We want to know what the density of that platinum is. So we need to take the mass of our atoms, divide it by the unit cell volume, and then we will get our density. So first, mass of atoms. So how many atoms do we have in a face-centered cubic cell? Face-centered cubic, we have 8 atoms on our corners. Each corner piece shares 1/8. Shares between 8 unit cells, so we get 1/8. We have 1 atom on our corner pieces. Then we have 6 faces, each that have an atom, and each which is shared with another, so we get 3 from there. So we have a total of 4 atoms. Each one of those are platinum, so they have a mass of 195.08 grams per mole. Right? So that's if we have a mole of atoms. However, we only have 4 atoms, so we're going to use Avogadro's number. 1 mole is equal to 6.022 times 10 to the 23rd atoms. This will cancel out our atoms, this will cancel out our moles, and this will give us 1.30 times 10 to the negative 21 grams. Okay? Now we want volume of our unit cell. Here, we're going to take A and cube it. So A for a face standard cubic is 2 square root of 2 times by R. Okay? Our R, in this case, is 139 picometers. We must convert that into centimeters. So 139 picometers. There is 1 times 10 to the 12th picometers per 1 meter. And then there are 100 centimeters per meter. That'll cancel out to give us 1.39 times 10 to the negative 8 centimeters. We'll then put that in for radius, cube our A, and we'll get our volume. So we have 2 square root of 2 times by 1.39 times 10 to the negative 8 centimeters. And we're going to cube this whole substance, and we get a volume for our unit cell of 6.08 times 10 to the negative 23 centimeters cubed. Now we figure out our density simply by taking our mass divided by our volume. So we take 1.30 times 10 to the negative 21 grams divided by 6.08 times 10 to the negative 23 centimeters cubed, giving us 21.3 grams per centimeter cubed. We should expect a volume of greater than 1 for any of our metallic solids, and usually between 5 and 20. So this is a fairly reasonable density. Let's try again. We have iron, we have a body-centered cubic structure, and we have an edge length of 2.866 angstroms. Remember our edge length, A, right there. So we've already got our A, we don't have to determine that. Now we just need to figure out, from the information we're given, how many atoms we have in our cell. With a body-standard cubic, we still have our 8 corner pieces, so each of them are an eighth, giving us 1 total, and then we have 1 atom in the center, completely in the unit cell, so that gives us total atoms. So we take our mass of our iron. We have 2 atoms. For this, we have a mass of 55.85 grams per mole. And again, we still need Avogadro's number, so we can cancel out moles and just give us grams. So 6.022 times 10 to the 23rd atoms, giving us a total mass of 1.855 times 10 to the negative 22nd grams. Then we do our volume of our unit cell. .866 angstroms. Every angstrom is 1 times 10 to the negative 10 meters. And then there are 100 centimeters per meter, giving us 2.866 times 10 to the negative 8 centimeters. We're then going to cube this, because this is our A value, giving us 2.345 times 10 to the negative 23 centimeters cubed. And then our density, mass divided by volume, 1.855 times 10 to the negative 22nd grams, divided by 2.345 times 10 to the negative 23 centimeters cubed, gives us 7.880 grams per centimeter cubed. Again, reasonable value. Okay, let's look at packing efficiency. Packing efficiency is going to be how efficient we can put atoms together. So remember, atoms are spherical in shape. We kind of consider them as rigid spheres that don't move or pack or move or like squish. Not entirely true, but for this purpose, we're just going to consider them rigid spheres. So think about marbles. What's the closest we can get those marbles together is given by our packing efficiency. So we take our volume occupied by our atoms, divide it by the volume of our unit cell to get our packing efficiency. So our volume of atoms, volume of unit cell. So this is going to be A cubed for the volume of a unit cell. Volume of our atoms, we take 4/3 pi r cubed, and we're going to multiply it by our number of atoms. So take each atom that we have, take the radius, figure out the volume of the individual one, multiply it by each atom in the cell itself. Okay, so let's try. We want to determine the packing efficiency of a face-centered unit cell. So it really doesn't matter what face-centered unit cell we have, it'll all have the same packing efficiency. So we're going to just use a generic R for radius because the radius will be the same in our volume of our unit cell as when we use it for the volume of our atoms. So first thing we want to do is figure out the volume of our atoms. So how many atoms do we have in a face-centered unit cell? The answer is 4. We have 3 on the faces, 1 on the corner, giving us a total of 4 atoms. And we're going to multiply this by 4 pi r cubed divided by 3. So our volume of a sphere. Multiply this out, we get 16 pi r cubed divided by 3. Again, we're going to have r cubed within the actual unit cell volume, so they'll cancel out. So our unit cell volume, we're going to take our A value, which is 2 squared root of 2, r, in the case of a face-centered cubic cell. We're going to take this whole thing and cube it to give us our volume. This gives us 2 square root of 2 cubed r cubed. Now our packing efficiency. We're just going to take the volume of our atoms divided by the volume of our unit cell and divide it out to get our packing efficiency. So there's the volume of our atoms, the volume of our unit cell, and as I said, we have r cubed for both, so those will cancel out, giving us 16 pi. I'm going to put the 3 on the bottom here, and we get this value right here. If we divide all of this out, we get a packing efficiency of 0.74 or 74%. As I said, that'll be the same for all face-centered cubic cell. We can do the same for body-centered and primitive as well. Okay, so how do unit cells for metal atoms differ from unit cells for ionic compounds? With a metal, we only have one thing, right? It's all the same thing. It's going to make up our unit cell. It's going to take on one of those unit cell packing types. So face-centered, body-centered, cubic. So those 3 pieces. So they'll take on face pieces, body pieces, and corner pieces. Ionic, we still will be using the same packing efficiency, but it'll only be for our anions. So anions themselves are larger. Anions will always be larger. They're larger because they have more electrons. So they have kind of spread out. The cation is smaller because it has fewer electrons, so it's going to pull those electrons closer to the nucleus and be smaller. So if we have our anions, they will always take up, or with our anions, they will always take up the spaces of the unit cell packing densities or packing arrangements that we've seen so far. So the unit cell will be made up of anions. So we'll either have a face-centered cubic structure for anions, body-centered cubic structure for anions, or our primitive cubic for our anions. And then what's left over is spaces where the cations can fit in. These empty spaces, they're called interstitial holes or just holes. That's the empty space left over by our anions, and that's where the cations themselves will fit. The smaller the cation, the smaller the cation hole. The larger the cation, the larger the cation hole. So we look at the ratio of our cation to our anion to determine what size hole our cations can fit in. The types that they can fit in are either a cubic, tetrahedral, or octahedral hole. The cubic is going to be the largest, so it'll be the hole for the largest cation versus anion. Octahedral will be the smallest. Tetrahedral will be the smallest. And then this will be in the middle for our octahedral. Okay, so our ionic solids themselves, remember we've got alternating cations and anions, so every cation is surrounded by anions, every anion is surrounded by cations, and they're held together by ionic bonds. It is very specific that our cations are surrounded by anions are surrounded by cations. We do not have anions touching each other, we do not have cations touching each other. That is going to cause repulsion and make an unstable structure. So we determine the number of ions that surround an oppositely charged ion based on the crystal structure itself. So we'll look at how we do that. So remember, we have ions beyond count, but we always give our chemical formula as the empirical formula, so our smallest whole number ratio. For instance, sodium chloride, 1 sodium to 1 chlorine. Magnesium chloride, 1 magnesium to 2 chlorines. So even though we have billions of magnesiums and chlorines, we use the whole number ratio, smallest whole number ratio, to represent the chemical formula. Ionic solids themselves are brittle, hard, and high melting. They're brittle because they're made of ionic bonds that keep everything in a very rigid arrangement. We can't move the atom or the ions like we did with our metal atoms. The metal atoms were very flexible. They can just kind of float through their sea of electrons. Here, if we shift any of our ions, we're going to get anions touching anions, cations touching cations. Not good. They are very hard substances, and they are very high melting. They're high melting because we've got a substance where we have to melt, or we have to break ionic bonds in order to melt that substance. Okay, so just said a second ago, but why are ionic solids brittle? So ionic solids are brittle due to their attractive forces, but why? So the strong attractive forces allow the layers of ions to shift easily. They cause a compound to vaporize easily. They hold the layers of ions in relatively fixed positions, or they keep the surface dull. So, ionic solids are brittle because the strong attractive forces are going to be keeping everything in a very specific rigid arrangement. So they hold the layers of ions in relatively fixed positions so that we don't have anions touching anions, cations touching cations. In this class, we're going to be looking at binary ionic solids. We've looked at ionic compounds that have polyatomics, but we're not going to look at that for this particular chapter. So we only have 2 ions within our solid. Our lattice structure is determined by the anions, and the cations themselves will fit in the interstitial holes. Now, what we want to do to have a good structure is maximize the number of nearest neighbors. So we want to maximize our coordination number. But of the opposite charge. But we want to keep a charge balance, and we don't want to have ions with the same charge to a touch. So if we have something like this, there we have a small cation surrounded by a lot of anions. The anions are too big relative to the cation, so we get a structure that is unstable because the anions are touching. As we increase the size of our cation, we get a more stable structure. with this type of coordination. And then here we have the most stable structure with this larger cation because we are now pushing our anions further apart. So it's going to be a balance between getting as many number of nearest neighbors as well as not having like charges touch. So the cation holes themselves are going to be the holes where our anions left behind for our cations. We have three types: cubic, which is our largest, octahedral, middlest, and tetrahedral, smallest. We can take a 1-to-1 mole ratio of cation to anion and very easily determine the hole type, or we could just use our radius ratio. So we have our cubic hole, which is for large cations. So it basically, what's shown over here, it's basically a body center piece. It's not actually a body center piece, but that's what it looks like. The center atom is considered a hole, so it's not the same thing as a body-centered cubic, just again looks like it. So if we look at this center atom right here, we can see that it has 8 anion nearest neighbors. So we would say that that cation has a coordination number of 8. And we generally only look at the cation or the coordination number for the cation, unlike with metallic solids. With octahedral and tetrahedral, octahedral is a little bit smaller than the cubic hole, so this is for medium-sized cations. Here we have a coordination number of 6. So if we look over here on the right, we see that we have 3 cations and then 3 anions and 3 more anions, and the cations right in the center of those. So we have the 3, and then rotated we have 3. So kind of like that, and they kind of keep the cation right in the center, and it forms an octahedron, which is why it's called octahedral. Then tetrahedral is for our smallest cations relative to our anion. So it's the smallest ratio, so it's going to have the smallest coordination number. It's going to have a coordination number of 4. So you can think of 3 anions, the cation in the center, and then an anion on top. So it makes a little tetrahedron or tetrahedral. Let's visualize these real quick. Here we have chlorine forming a face-centered cubic cell. We can see it because here are our corner pieces. So our corner pieces are always going to be our anions. And then there are the faces with chlorines as well. So this is a face-centered cubic cell for our anions. Then our cations are going to fit in the spaces left behind. In this case, they're going to fit on edge pieces and right in the center. So if we look at this piece right here, we can kind of see what type of coordination we have. So when we count out how many anions are surrounding this cation, we see we have this one, this one, this one, this one, this one, and this one. So it's a coordination number of 6. Our tetrahedral holes, a little bit smaller, as I said. Here, again, we have chlorine exhibiting a face-centered cubic cell, and then our cations are in a tetrahedral hole. Now, one thing to note, here we have all of our octahedral holes filled. Here we have some tetrahedral holes that are not filled. So that may be something you see in the future, how many of our tetrahedral versus octahedral holes are filled. In this case, not all of our tetrahedral holes are filled, because within here we see that we have, with these little boxes, there are 8 total of them, but only 4 of them have cations within them. So only half of our tetrahedral holes are filled in this particular case. But from here you can see we have 1, 2, 3, 4, so our coordination number is 4. So we can look at our structure to determine our type of hole and our coordination number, or we can use our radius ratio. So we're going to look at our cation size compared to our anion size. So literally the ratio, cation size divided by anion size in radii. And then from here we can calculate our radius ratio. Using this table, we determine what type of radius ratio we have, or what our radius ratio is, and what coordination number and hole type we have. Here, these three right here are going to be the cation holes that we have. If we have between 1 and 0.732 for our radius ratio, so again, cation radius divided by anion radius gives us our radius ratio. If that value is between 0.732 and 1, we get a coordination number of 8 and a cubic hole. If it is a little bit smaller, the radius ratio, we get a coordination number of 6, so between 0.414 and 0.732, octahedral hole, and even smaller between 0.414 and 0.225, we get a coordination number 4 and a tetrahedral hole. So let's see our ion size, how that affects our structure. So here we've got cesium chloride, sodium chloride, and zinc sulfide. In each case, our anion is about the same size at about 0.17, or 1.7, excuse me, and our cation radius is decreasing, so 0.181, 1.16, and 0.88. So from 1.81 to 1.16, we get, we get a smaller cation versus our anion, so our radius ratio decreases. As that decreases, we're going to have a decrease in our coordination number. And that's what we see. We go from 8 to 6 to 4. Let's also look at how stoichiometry plays a role. So if we're keeping our cation and anion sizes relatively the same, so sodium fluoride, magnesium fluoride, scandium fluoride, but we're increasing our number of anions, so we're increasing our anion to cation ratio, what we have is we have a decrease in our coordination number. So here we're going from 6 to 3 to 2, right? And we can determine what effect that'll have by looking at this formula right here. Number of cations per formula unit divided by the number of anions per formula unit will equal the anion coordination number divided by the cation coordination number. So if you have 3 of these pieces of information, you can figure out the next. So you're looking at your formula unit itself. So in this case, we'd have 1 to 1. So our cation and anion coordination numbers will be equal. Here we have 1 to 2. So we're going to decrease our anion coordination number, and then 1 to 3, decrease it even further. Let's see how you guys are following along so far. So we've got titanium 4+ and oxygen 2-. We have radii of 0.60 angstroms for titanium 4 and 1.40 for oxygen 2-. We want to figure out our radius ratio, and from there determine our cation hole from that information. So we take our radius of our cation, which is 0.60, divided by the radius of our anion, 1.40. Both of them are in angstroms, so those will cancel out. And that gives us a radius ratio of 0.429. From our table, we would see that this is an octahedral hole, which means that we have a coordination number of 6 in this case. Okay, let's try again. So we have the following unit cell right here, and X is within the cell, so that one right there. Y is on the corner, so that one right there. We want to know what the formula of this compound is. So we need to look at our X and our Y. First of all, which one's our cation, which one's our anion? Our anion always makes up our unit cell, so it's going to be the ones that are on the corner. So this is our anion. X is our cation. Okay, so now we figure out which one is which. We need to figure out what our empirical formula is here. So we've got anions on each of the corners. There are 8 total corners. Each one accounts for 1/8 of an atom. So we have 1 of these. Our cation is completely within the unit cell, so it is going to also account for 1 atom. So we have a 1-to-1 ratio of our anion to our cation. Okay? So in this case, we would have a chemical formula or empirical formula of X, Y. Our X should go first because that's the cation, our Y should go second because it's the anion. Also, some information you might glean from this is also our coordination number of our cation, which is 8. Also, from that information, we should know that this is a cubic whole. And our anion is primitive cubic. So these are also pieces of information that you should be able to come up with from this unit cell structure. Okay. Let's move on to covalent network solids. So we're going to look at the structures of these, and we're also going to bring back band theory with this. Okay, so covalent network solids, we have a structure where we've got all the atoms in there covalently bound to other atoms within the structure. And it gives us an infinite three-dimensional structure. So we have atoms surrounded by atoms, and it just keeps going on in 3 dimensions. So this is like an ionic solid in that our chemical formula for our covalent network solid will be the empirical formula. So if we have a covalent network solid that is elemental in nature, such as carbon. So if we have a covalent network solid that is carbon, something like diamond or graphite or coal, all sorts of carbon solids, they are going to have just carbon as their empirical formula, so C. Silicon does the same thing. Silicon wafers for solar cells, you would just write as Si, even though it is a covalent network solid, so it goes in all 3 dimensions. Usually our covalent network solids that are elemental in nature, so only one atom type, are going to be in group 4A, so carbon, silicon, those types. We also have ones that are compounds, like SiO2, silicon dioxide, for like sand and quartz and stuff like that. These things themselves are hard. Covalent network solids are hard and high melting, usually very brittle as well, because they have rigid structures like ionic solids. High melting because in order to melt a covalent network solid, we have to break our covalent bonds. So, as I said, many of these covalent network solids, or all of these covalent network solids, have 3-dimensional structures, right? And as such, we're going to have, as we saw with metallic solids, and we see this with ionic solids as well, when we've got an extended structure, we've got a bunch of orbitals overlapping, and we form bands. So we're going to come back to band theory. So let's just look at some terminology that we didn't look at quite all that much with our metallic solids because they're not quite as important in understanding the terminology for this. But we have what's called the valence band. So this is where we have our overlapping bonding molecular orbitals. These are going to be lower in energy, and they're going to be filled with electrons. Then we have our conduction band. So this is our overlapping antibonding molecular orbitals. Higher in energy, unfilled, so we have no electrons within them, but we can conduct electrons into them, right? Which is why they're called the conduction band. Then we have our band gap, so that's the energy difference between our valence band and our conduction band, same as the HOMO-LUMO gap that we saw in molecular orbital theory, but now instead of between 2 discrete orbitals, we have it between bands of orbitals. With our metallic solids, there is no band gap. Our conduction band and our valence band are going to overlap. Our valence band and our conduction band overlap, so no band gap. So we can conduct electrons very, very easily between the two because there is no energy required to cause that process. With extended structures, ionic solids, covalent network solids, polymers, and nanomaterials, we're going to have band gaps. So anything that's an extended structure, not a discrete molecule, will have these band structures. So let's look at these. Like I said, with a metallic substance or a conductor, we have no band gap. So that's what we're seeing right over here. So they conduct electricity. A semiconductor has a small band gap. So this is a small band gap. Semiconductor material right here. These are metalloids and then some binary compounds, and these are able to conduct electrons by adding a little bit of energy in there. Then we have our insulator, which is a large bandgap material. Nonmetals are considered insulators, and most ionic compounds are going to be considered insulators in the solid state. Semiconductors can conduct electrons as long as energy is added into the system. So once we add electron or energy into the system, electrons can go from our valence band into our conduction band. Sometimes thermal energy is enough to cause that excitation of electrons from our valence band into our conduction band. Sometimes we need to add more energy in, depending on the size of the band gap. But generally there is enough to have some electrons go into the conduction band at all times, so we always have some electrons within our semiconductor's conduction band. We've got, like I said, we have the elemental semiconductors. So these are going to be things with 4 valence electrons. So stuff like carbon, silicon, germanium, and tin are going to be group 4A elements that form semiconductors. Inorganic semiconductors are going to have an average of 4 valence electrons. So we want 4 valence electrons total to make our semiconductors. So for instance, group 2B and 5A semiconductors, so zinc telluride, cadmium selenide would be examples. And then we have group 3A, 5A, so stuff like indium phosphide and gallium arsenide also will make inorganic semiconductors. When we're looking at the band gaps themselves, we generally think about what will cause the band gap itself to increase, and it's usually when we either have elements that are higher up on the periodic table. So if we have 2 things or 1 thing that is higher up on the periodic table, we're going to have a thing where we have all of those orbitals are going to overlap more, and that's going to cause a greater splitting between our bonding and anti-bonding orbitals. Okay, so remember, if we have greater orbital overlap, we're going to have lower energy bonding orbitals, higher energy anti-bonding orbitals. So the greater the overlap, the greater the split between that HOMO and LUMO, so the greater the band gap. We also, if we have something where we have a greater electronegativity difference between our elements and greater bond polarity, we'll end up with elements, or we'll end up with band gaps that are larger. So the greater the electronegativity difference between binary elemental or inorganic semiconductors cause us to have a greater band gap. Okay, so let's try, see if you were paying attention. Which of the following of these will have a larger band gap? So what's changing? We have gallium in all of these cases, going from nitrogen to phosphorus to arsenic and antimony. Which one, in this case, will have the largest band gap? So we don't have an elemental, so we're not worried about where one element is located on the periodic table. Here we have a case where we have differences in electronegativity. So nitrogen, phosphorus, arsenic, and antimony, we're looking at their relative difference in electronegativity to determine which one has the greatest electronegativity difference between our metal and our non-metal. In this case, it's going to be gallium nitride. Nitrogen is going to be the more electronegative, so it's going to have the greatest electronegativity difference between our gallium and our anion. So, largest band gap, right there. Okay, so a lot of times we'll have what's called an intrinsic semiconductor. So what we've just been looking at, where we have a semiconducting material that's just semiconducting based on its structure. We can also take and increase the conductivity of those semiconductors, intrinsic semiconductors, to make a material that is more semiconducting with a decreased band gap. So we take our host semiconductor, our intrinsic semiconductor, and we add materials in to make it an extrinsic semiconductor, a doped material. So adding a different element in to change the properties of the band gap of the native semiconductor material. We have two types. We have N-type or negative type. So we add an element in that has more valence electrons in the host material. For instance, phosphorus. Into a silicon host lattice, phosphorus has 5 valence electrons, silicon has 4 valence electrons. So phosphorus has a greater number of valence electrons, and it'll add what's called donor levels in. So we have our, right here is where we see this. So these donor levels are going to be the valence electrons energy levels within this substance, and then our band gap decreases. So we've added in a donor level, decreasing the band gap. We can also have a p-type or a positive type, so we've added an element in that has fewer valence electrons, gallium for instance. Gallium has 3, silicon has 4. So here we have an acceptor level, so right here. So this is going to be a level with no electron density within it. So we can add electrons there and have a new band gap that is smaller. So we've produced positive holes within the valence band to have an acceptor level, which decreases our band gap. Okay, so what type of substances must be added in order to produce donor electrons, and what must be added in order to acceptor holes? What type of doped semiconductor substance do we have in each? So these are N and P-type semiconductors we just talked about. So donor electrons, we need to have additional electrons, so we need something with greater number of valence electrons. If we add those in, we get a N-type semiconductor. If we want to have acceptor holes, it has to have fewer electrons, so fewer valence electrons than the intrinsic semiconductor material. We call this a P-type semiconductor, or positive type. Let's move on to polymers. We're going to be super quick with this one. So polymers are molecules with high molecular weight made by joining smaller molecules called monomers. So we add monomers together to get a polymer. We generally classify 2 types of polymers, or look at 2 types of polymers in here. Addition polymers. So we break a bond to form a new bond with a new atom, a new monomer. So we break the bond of one monomer, break the bond of another monomer to make a dimer, and go on out until we make a polymer. In that case, we're just breaking bonds. We're not removing any atoms. So our monomer will have the same molecular weight as the empirical formula of our polymer. Our condensation polymers are when we take a small molecule and remove it to produce a new bond. That small molecule is going to be water. In most cases, not always, but the ones we're going to look at, we're removing water to form a new bond between 2 monomers, and that'll eventually keep going until we make a polymer. Let's look at the reactions a little bit more in depth. So we have our addition polymerization, what's shown up here on the top. So ethylene, when it breaks that double bond, when next to another ethylene molecule, it will form a new bond between the 2, and it'll keep going, forming new bonds until we get what's called polyethylene. So taking ethylene, making a polymer, and it'll keep going until something is added to quench the reaction. We take a double bond carbon-carbon, or a carbon-carbon double bond. We break the double bond, form new carbon-carbon single bonds with other monomer units, again, until we make our large polymer substance. So we would classify this polymer as C, and then we put brackets around it, like so, with our hydrogens in there. And our polyethylene structure, put a little N to indicate that that is repeated for however many times. So hundreds of times that could be repeated to make our polymer unit. We also have a condensation polymer. Condensation polymer is when we make a polymer doing a condensation reaction. So we condense out a molecule, particularly water. So we take this, remove water. So generally, it's going to be between an amine or a nitrogen hydrogen, and a carboxylic acid. So that OH and that hydrogen are removed to produce water, and we form a new nitrogen-carbon bond. This can also be done with an alcohol, OH, plus our carboxylic acid. These are removed to produce water, and will produce a oxygen-carbon bond. So you're looking for one of these types right here to determine if it's a condensation polymer. Here are some addition polymers and some condensation polymers. Again, if we're trying to find our monomer unit, we just kind of take polypropylene, for instance. We take the structure we see, within our brackets, so that is our monomer unit, or can be considered our empirical formula, and we remove the stuff that's extra, and we put a double bond between our carbons. So this would be our monomer. With condensation polymers, it's a little more difficult. What we're looking for is a nitrogen-carbon bond or an oxygen-carbon bond where the carbon has a double bonded oxygen to it. And we break the bond between there like so, producing a putting a hydrogen on the nitrogen and oxygen, putting a hydroxide on the carbon with the double bonded oxygen on it. And we'd have to also put a hydrogen here and a hydrogen here. So we can say this is NH2R NH2 as one of the monomers, and then the other monomer would be that OH with the carbon, oxygen R prime, oxygen, carbon, oxygen, hydrogen. Like so. Oh, sorry, OH, I lied. Okay. Let's look at the properties of these. So these are not going to be straight line material, and the more the chain grows, the more twisting that's going to occur. The more twisting that occurs, kind of the more locked in place these things can become. So higher melting points for these substances, higher boiling points for these substances, harder the material. Now, if we have greater lengths of chain, we will have usually a variety of molecular weights. So if you're starting off small, you might get a fairly regular, less variety within your molecular weights, but the longer the chain, the more variety you will have. But all of them will have variety in their chain lengths because this is not, the synthesis of these polymers are not perfect. They're considered flexible materials because they're just kind of held together by intermolecular forces. But they are very long, so they're stronger intermolecular forces, very strong, usually London dispersion forces. And we're looking at what these flexible materials, we usually call them plastics, because they are, because of the flexible material. They're not always plastics. Polymers are not always plastic materials, but usually. If we have short grain order, we can get crystallinity within our solid, but we can also have amorphous materials. So some polymers will be amorphous, plastic-like, and then some of them will be more crystalline, so more rigid structures and usually more brittle. We can kind of change our properties by taking our substances and stiffening them, which will strengthen them. It'll also make them more brittle. But when we do that, which the process is called vulcanization, we add short cross-linked chains holding our different substances together, as we can see here. So we can have our long polymer chain and then do vulcanization to add some cross-linkings in between the chains in order to get a stronger material. Okay, let's look at our learning objectives for this section. So the formation of what type of polymer involves the elimination of a small molecule. So we have addition and we have condensation. Addition, we're going to break a double bond to make single bonds with another monomer. Condensation is when we take two monomers, we react them and remove water. So this would be condensation. And again, that small molecule is generally water. And last part, we'll look at nanomaterials. So these are substances, these are structures that have at least one dimension on the nanometer scale, so 1 to 100 nanometers. We have sheets, which have one dimension in the nanometer scale. So this would be an example of a sheet. So this is one dimension, but the other two dimensions, or this is nanometer dimension, the other two are not. We have rods, so this one right here, where we have 2 dimensions in the nanometer scale. So we have basically the height and width of the tube, and then the length of the tube would not be on the nanometer scale. And then lastly, we have particles, which are most of the rest of these, which have all 3 dimensions on the nanometer scale. Semiconductors on the nanometer scale is when we have a small nanomaterial made out of a semiconductor. So we take a semiconductor and we make length, width, height on the nanometer scale. So we've got something where we've got fewer orbitals than in a bulk material. So small molecules have discrete orbitals, bulk materials have bands, and we want to know if we have a semiconductor on the nanoscale, at what point do we switch over between discrete orbitals to bands? Usually that's going to be between 1 and 10 nanometers. Quantum dots themselves, which is one of the most common semiconductors on the nanoscale, are semiconductors in this scale. So because of this, we get some really interesting properties. Here is cadmium selenide, which we know is a semiconductor material. The only difference between these substances here are their size. This is going to be around 2 nanometers. This is going to be around 7 nanometers. So we are increasing in size as we go in this direction. So what's happening? To determine that, we look at this equation. So the bulk, or the nanomaterial band gap, Eg, is related to the bulk band gap, so Eg bulk. They would be equal to each other if we did not have this crazy term over here. So what happens is as we increase our radius, we're going to decrease this term. When we decrease this term, our bulk and our nano are much more similar in size. So the band gaps are more similar. As we make this smaller, this term gets larger, and our nanomaterial band gap gets larger. So that's the most important terms that you need to know from here is the band gap of our nano, band gap of our bulk, and the radius of our nanomaterial. So what we get from this is as we increase size, we are going to decrease our band gap, or as we decrease size, we're going to increase our band gap. And that's what we see over here on this spectrum. So we see with smaller size, we are blue shifted, which is higher in energy. Larger in size, we're red shifted, which is lower in energy. Some other terms within there, we have epsilon, which is the relative permittivity. Epsilon naught is that permittivity in a vacuum, and that's just the ability for a material to resist an electric field. The other term over here is the particle in box confinement energy, when we're talking about an electron and the hole that's left behind after it's been excited. It's just going to be talking about the attraction between that electron and that hole. Most of that, those other terms are unimportant for our general understanding. Just what we want to know is that as we decrease the size of our nanomaterial, we're going to increase the size of our band gap. And if we think about this in terms of molecular orbital theory, we have fewer orbitals that are overlapping, so they're going to spread out a little bit. Okay, we have our nanometals. So here we're taking metals and we're finally dividing them into smaller sizes. So what happens as we do that is we get the color of that material being dependent on the size. So over here we see gold from 5 to 90 nanometers. It's kind of a complicated understanding, but again, we can kind of think about the fact that we have fewer orbitals overlapping as we get smaller and smaller, so we start to actually form a band gap with nanometals. When we get small enough, we don't have enough orbitals to overlap anymore, and we get actual colors seen as opposed with just the shiny color we're used to seeing. We also have nanostructures of carbon. So this is the last thing we're going to look at, just because they're super fun. So we've got a couple that we're going to look at. We're going to look at Buckminster fullerene, or buckyball. That's this right here. We call it C60. This was discovered back in 1985. And then we have carbon nanotubes, this one right here. They were discovered in 1992. And there's also graphene, which we're going to talk about in just a second, in 2004. The neat thing about C60 is it can absorb most of the solar spectrum. So they're trying to use it in photovoltaic type processes. Carbon nanotubes are semiconductor materials without adding any dopant in there. So while a lot of carbon structures are extended structures or covalent network solids, they are not semiconductor in properties. They have a band gap, they're more insulators. But as you get smaller and smaller, you get a thing where you actually have semiconductor materials. And the nice thing about carbon nanotubes is they have really good mechanical properties. So they're really strong. They're the strongest one-dimensional material. And one-dimensional because there's only one dimension that's not in the nanoscale, right? So you can actually pull on those. We have some other ones. We have graphene right here. Graphene is just sheets of graphite. They actually were able to get sheets of graphite first by taking tape, just some Scotch tape, and taking pencil and just doop, and they had a sheet of graphite. It was really neat. It is a very high tensile strength structure. It has electrical conductivity. It is transparent to the eye, and also to light. And it is the thinnest two-dimensional material in the world. Again, two-dimensional because two dimensions are not in the nanoscale. The last thing we want to look at is nanodiamond. So it has the same structure as regular diamond, but it is on the nanoscale. So, like 20 atoms as opposed with millions of atoms. It has excellent optical properties, mechanical properties, and very high surface areas. So we can attune the surface structures here. So those are just some of the interesting nanostructures of carbon. Look at some concept checks with this within our nanomaterial. So we want to know if we have a band gap of 2.26 eV electron volts. What is the color of light that the bulk material emits? And so we want to figure out our wavelength of light. And we want to assume the emitted light is equal to the band gap. So as you excite it, when it relaxes back down, it'll emit that energy light. So 1 eV, or electron volt, is equal to 1.602 times 10 to the negative 19 joules. That would be a value you would be given. So we can convert that 2.26 eV into joules using that information. And this gives us 3.621 times 10 to the negative 19 joules. Okay, so now we're going to take this energy and put it into our energy equation. So the equation that relates energy and wavelength is energy is equal to Planck's constant times by the speed of light divided by the wavelength of light, where the wavelength of light is equal to hc divided by energy if we want to rearrange. So wavelength is equal to 6.626 times 10 to the negative 34 joules times by seconds. And this will be times by 2.998 times 10 to the 8th meters times by seconds to the negative 1, so our speed of light, all divided by 3.621 times 10 to the negative 19 joules. This gives us a wavelength of 5.486 times 10 to the negative 7 meters. We convert this into nanometers, we get 549 nanometers, which is green. Okay, let's try one more. When the size of the semiconductor particle or crystal decreases, what happens to the band-gapped energy? So, we're going to decrease our size of our particle, decrease our number of energy levels. This will result in a band-gap energy that increases because we have fewer energy levels within.